Okay, in the last video we looked at how to convert a system to a second order differential equation, and now we want to see if we can go backwards. And so suppose I write down this, let's see, how about y double prime plus 2y prime plus 5y equals, how about cosine of t? Well, the idea here is that I can let x1 be equal to y and x2 be equal to y prime. Then by finding a system of differential equations for x1 and x2, I can write my original differential equation in terms of a system. So by that I mean, if I take x1 prime, right, that's going to be y prime by definition, and then y prime is actually x2. Good, so therefore I have x1 prime is equal to x2. Similarly, x2 is y prime, right? So what would y double prime be? Well, that would be x2 prime. So converting my equation, y double prime plus 2y prime plus 5y equals cosine of t. I'm just going to rewrite this in terms of x1 and x2. So this would be x2 prime, right, plus 2, and then y prime was x2, and then y was x1. And then the cosine of t, I could just bring it down. Okay, but now I can solve this for x2 prime, right? So x2 prime would be, now when you've got variables in order like this, go ahead and put them in order. So this would be minus x1 minus 2x2 plus cosine of t. Good, so this is our system of differential equations that corresponded to that. Now notice that I could have been tricky. I could have replaced the t with another variable. So in fact, I could have let x3 be equal to t, and then my differential equations would be what? x1 prime equals x2, x2 prime equals minus x1 minus 2x2 plus cosine of x3, and then x3 prime would be 1. Yeah, so this is one way to, so you can actually rewrite any differential equation into a system of autonomous differential equations. It's kind of a cheat, right? Because autonomous means that time is not specifically defined here, but actually x3 is t, so it's just kind of a sleight of hand there. Okay, so typically we're going to how about maybe before I leave this, how about let y triple prime plus y prime plus y double prime times cosine of t, I'm not very random today, equals 0. Convert to a system of first order. And so notice that this has a third derivative, and so we will have to use an extra variable for that. Now we didn't say autonomous, otherwise I'd have actually 4 variables. Oh, let's go ahead and make it autonomous just for fun. So we'll let x1 be equal to y, x2 is y prime, and x3 is y double prime. We'll need those 3 variables to convert a third order differential equation. And then for fun we said that x4 is equal to t to get rid of the autonomous part, or to make this system autonomous. Okay, so now let's see if we can write down our system directly. x1 prime is equal to y prime, which is x2. x2 prime is equal to y double prime. Y double prime is x3. x3 prime is y triple prime, right, which is here. And so move these over to the other side. And so this is going to be x1 times x2. And then this is going to be x3 times cosine of x4. Good. And so this is now my system of differential equations. Excellent. It's kind of fun to do that. Good. But the main point here is that so we can convert especially second order differential equations to a system of two variables, right? So therefore what I'm trying to say is that we can rewrite ay double prime plus by prime plus cy equals 0 into a system that looks like x1 prime is equal to, I don't want to use the same a hat x1 plus b hat x2, and x2 prime equals c prime x1 plus d prime x2. Good. And so these are the systems that we're going to be working with. And so when we're trying to solve these, we can just go ahead and convert them into second order differential equations. Good. All right. Okay, I just wanted to talk briefly about a third technique that we've been kind of working through. So our first two techniques were the conversions back and forth technique. Actually, this isn't really a formal technique. This is more of an observation. Remember that in Calc 3, we're able to compute dy over dx given x of t and y of t as our, let's see, we can use brackets, I guess, for Calc 3 notation. Do you remember how to do that? Well, dy over dx can be written as dy over dt divided by dx over dt. Right, so here you could differentiate your x and your y to figure out what your derivatives are, and you could formulate dy over dx. Well, notice that what we're doing is that when we have a system of first order, we have dx over dt is equal to some expression in x and y, and dy over dt is some expression. This is when we get an autonomous system. Okay, and so given these, then we can convert this to a single first order differential equation, right? Do you see what we're going to do? We're going to take g of xy divided by f of xy. T is now gone. No t here. And so in the notes I call this an unparameterization of the of your function. So we're converting it from a parametric set of equations to a single first order differential equation. And so hopefully we can find a technique in chapter 2 that will solve this differential equation. Okay, so let's just do a quick example. So we'll just use our initial example. That was x prime equals minus y, and y prime is equal to x. Right, so therefore dy over dx is equal to minus x over y. What kind of a differential equation is that? Let's see. It's a homogeneous differential. Well, that's okay. We don't need to convert it. We don't need to make it a homogeneous differential equation, though. Remember that from chapter 1 or chapter 2. It is also separable, and so we could write y dy equals minus x dx. And so we can solve this directly. y dy equals the integral x dx. So we have 1/2 y squared is equal to minus 1/2 x squared plus c. But of course we could simplify that, right? Multiply through by 2. Bring the x squared over to the other side. And what do you see? Well, I'm going to convert my 2c into an r squared. And now we see that the solution to our differential equation is a circle of radius r. But you see that this is not parameterized. right? So that's what we mean by getting rid of the parameterization, right? You go from having um, oops, you go from having x and y defined separately on the circle to having an expression of x and y together. So this is graphing x and y. Good. All right, so I'm going to stop here. I think we'll stop here for this section. And in the next section, we'll talk about a different technique for solving a linear system um, that uses something called an eigenvalue. All right, see you then.